tomorrow.
I wouldn't be so sure. And it's supposed to be in the 60s tomorrow, so.
I'm going to be here.
Cool, I'm going to be here.
Good, I hope so.
Are celebrating with their free pizza party from the student involvement fair.
Oh, cool, awesome.
That's pretty cool.
Yeah. If you didn't turn in your extra credit sheets and you have them, go ahead and turn them in. I put a 0 as a placeholder, but I'll adjust it. So I'm still grading PA5. It's going to take me a couple more days to get through all of those because I'm also writing exams and stuff. But PA5, you know, looks really good, and we already saw presentations, and everybody got it to work. A few people didn't have the full recursive solution, so there's some edge cases that break it. The two things I've seen most frequently, though, that cost a few points. One was just not checking as you're parsing the knapsack.data file, not checking to make sure that it's valid. So if it's supposed to have a value, which is an integer, and it's not an integer, you should notice that and say, you know, this is an invalid file. And some people's programs just use scanf and don't check to see if it's an int, so you just get kind of random values in your knapsack, so that's like a few points. The other thing, and I'm not sure exactly where this is happening, but one of the tests I'm doing is where your knapsack.data file, the lightest item might be, say, 10 pounds. And if you run the knapsack problem and you say my bag can only hold 5 pounds and all the items weigh more than that, it should say, okay, your max value is 0. And that's actually like really confusing some people's programs. So there's some initialization or something, or some edge case that's not being handled. And in a few cases I'm getting, you know, inventories with like 80 numbers in them. Put in 2.5 million of this item and put in -3 billion of that item, and so on. So it's some kind of initialization thing. And so those are both, you know, just a few points, but I'm working through all the PA5 submissions, but they look really good. So I think people are good on knapsacking and those kinds of recursive solutions to problems. So any questions before we just kind of like start going through general review from the 8 of you?
Oh wow, that's not many people here.
There's not.
No.
They're all out getting pie.
Is it even open yet?
It just opened. There's a big line.
At 11.
Why are we here?
I know.
No, I'm fine.
There-
Do you want one for it?
There should be pie at 11:50.
Okay.
Yeah.
It runs until 2.
Runs until 2. We could get out 5 minutes early to beat the between crowd rush, because we got 2 days to review.
Since we're going to be reviewing, would it be possible to give like very small examples of the general subjects we're going to be going over?
Small examples of like
For the different, essentially, chapters that we went over, the
Mhm.
different functions we went over, like, more so along with like the trees and other values of like that as refreshers.
Mm-hmm.
Just maybe small pieces of code or small programs you might have saved away or something. I don't know.
Okay.
Just like examples going through it as well. If possible.
Yeah. We can talk about some specifics. You've got a lot of them already in your programming assignments and ODPs and such. But we can try to hit some specifics, or, you know, if we talk about something and you think that would be a good place for a specific, just go ahead and ask, and we'll work through it like that. So part of this is kind of the same as what we had for the midterm, right? Because all that stuff from before the midterm is still fair game. But structures, right? So you know how to define structures. The structure statement. Structures are composite variables. They have fields associated with them. Oftentimes we deal with pointers to structures in this course. So we'll have structure name star variable, and then if you want to access the fields of a structure, so structure, mystruct, var, we could say var dot field. And if you have a pointer to a structure like pvar, then we can't say pvar.field because pvar is not a structure. Pvar is a pointer, right? But star pvar, the thing that it points to, that's a structure. So that we could say .field. But we don't write that. We use this weird shorthand, which looks like this. And so you think of the arrow as saying, take the thing that pvar points to and give me that field. Right, so it means the same thing as that, but it's dereferencing the variable before we grab a field.
So, I have a question about that. What would be the difference between having the asterisk on the inside of the parentheses versus the outside?
I don't know if it's valid on the outside.
I was gonna say, I don't know if it works, but like...
I don't even know if the parentheses are needed, but let's find out.
Oh, fun.
Yeah. I just put them in because I'm kind of like paranoid about parentheses.
I've heard us to be overcautious, except in certain situations.
Yeah, I agree with you. Guess we need a struct.
My strict,
Yeah, my struct.
my stuck, my
Yeah. All right. So this also brings up the next thing on there, which is how we allocate space for structures. So if you have a variable that's actually a structure, you can just say struct my struct variable name. It's no different from integer I, right? If you have a pointer, that's like saying integer star I, right? You can't start using I at that point because it's not pointing anywhere in particular. So if we have a pointer to a structure, what do we have to use to make it point somewhere? Yeah, you got to do a malloc, so. And we'll use size of and say what type of variable is. So it's a type my struct. How many ways can I spell my struct today? So that's definitely going to give us an error. So I'm predicting that only that third one's going to actually give us an error. Okay.
So all of three of them layers.
Yeah, so let's get rid of this one because we know that's totally bogus. That looks fine. So yeah, it actually complains about that. So I think it's trying to do this first and then use the star, so there's an order of operations. So yeah, the parentheses are actually essential there. But it knows what I mean. Right, did you mean to use an arrow?
So they're trying to read pointer.x and then dereference that?
Sorry, say again?
That weird one with the star pointer.x, is it trying to read pointer.x and then dereference it?
Yeah.
I don't think the second one was the error.
Yeah.
The pointer, and it would work.
Yeah, it would do it.
Yeah, I feel like that's kind of horrible code.
Yeah.
The first one,
Yeah, line 12. All right. So yeah, so either parentheses or the arrow. Well, that's good to know. All right. Let's see. Where were we?
Is there an advantage to using pointer structure over an array allocated structure,
Yes.
or vice versa?
You mean using this instead of that?
Yeah, and using the other instead of a pointer. Are there advantages and disadvantages to either one?
So like when you're doing a linked list, right, and you're trying to create new nodes, you gotta have a pointer to a structure. You gotta have a pointer to a node. If I do like struct node temp, right, and try to use that for a new node I'm inserting, right, it's not actually a new node. And I can't assign it a new address with Malloc.
Right.
So we pretty much always use pointers when we're dealing with dynamic things that we're creating on the fly in memory.
Pass just the structure itself, doesn't it pass like a copy of that structure?
Yeah, if you pass the structure itself, it's still passed by value, so it passes a copy of it.
And that's why we can't like rewrite pointers.
And if you change a value in there, it should not change. But if you pass a pointer to it, right, and then you use the arrow, you're changing the thing that it's pointing to, which is what the original program was pointing to also. All right, so allocating memory, that's just Malloc, accessing fields, and arrays of structures are just like arrays of anything else. You can say structure name, variable, bracket 10, and it gives you 10 of these. And we don't do a whole lot of that, but you can. So linked lists. Oh, let me tell you about the exam up front first, so you can have that in mind while we're going through these. Let me tell you about the exam in general. So 110 minutes, your usual 8 pages of notes, and 10 questions. Okay, so 4 full programming questions, 1 question that's got a little bit of programming in it. So 4 or 5 things where you're going to be writing programs. And then the rest, the other 5 questions are all basically doing things like what you've done on the board in class. So things like, you know, here's a tree, insert a node and see if it's balanced and adjust it. Or here's a heap, add something to it. Or here's a heap-shaped collection of numbers, heapify it. Or here's a picture of a trie, tell me what things are stored in there, or add something to the trie. Or here's a hash table and a hash function, and some words, show me where these words would get stored, and so on and so forth. Okay, so things where you're going to be drawing pictures or manipulating data structures on paper and so on. So half of it is that, half of it is programming. There's no multiple choice, fill in the blank, short answer, true, false kinds of stuff. Okay. Or very few. Yeah?
Does all that include that complicated rotating tree stuff?
Yeah, so I want you to know how to do those rotations. So, and I mentioned this in the last section, I strongly recommend, but then I changed my mind. So I recommended that everybody have a copy of this, but not everybody got a copy of this because you're working in groups. So I'm going to print out copies of this and pass them out with the exam.
Okay.
Okay? And
That makes it less complicated.
that's less complicated, and then it won't count against your budget of notes, of pages. So, and I'll make sure everybody has access to that.
Would there be any chance you can provide example test on Canvas or something like that?
No, that I don't want to do.
Oh,
But you can look at the midterm for kind of the way that I asked you things. As far as, at the midterm, you had already done the linked list, so I asked you some linked list questions, but they weren't, write an insert function or write code to traverse a linked list. They were using what you know about linked lists and combining that with what you know about coding, basically. So it'll be things like that. So one of the programming questions will probably be kind of challenging. Okay, they're all 10 points each. But if I've got one on there that I know up front is probably going to be challenging. So if you get to one and it's like, oh, I have no idea how to do this, just come back to it, right? Budget your time. It's like 11 minutes per question, but some of these questions will be very fast, and some of them might take more time. So don't get bogged down. But the other programming questions will be similar to like kinds of things that I asked on the midterm, right? So either analyzing code, making changes to it, or you know how to do such and such because you did this in some programming assignments or some ODPs, but I want you to do something else with those concepts now. All right, so linked lists, you've done a bunch of things with linked lists. You did 2 programming assignments, you did ODPs, you used them in stacks and queues, you use them in the queue for the tree assignment, and so on. Some people use them in PA5, which was cool. So linked list, right? Pointers to node after node after node. Linked lists may have sentinel nodes, they may not have sentinel nodes, it depends. Okay, if you have a sentinel node, it's simply a handle to the first thing in your actual linked list. So if this is a sentinel, and your list is empty, your list looks like that. It's a sentinel node pointing to null. If you have a sentinel and a single node in your list looks like this. Okay, if you don't have a sentinel and your list is empty, your list is just null. There's no nodes. If you don't have a sentinel and your list contains a single node, it looks like this. So the sentinel, is, if it's present, is really just an extra node in the beginning that like never disappears. We never use the data value. We never insert anything before it, right? We just change what it points to. But it's a simplification of code. It's not an essential part of a linked list in general. So you know how to search, you know how to move through from node to node, how to insert, how to delete, and so on and so forth. Doubly linked lists, we haven't done anything with them in code, but they function exactly like a regular linked list. It's just that we have 2 pointers. So our list looks like this. Looks like that. And if you had to do something with this, like if you wanted to insert a node after, in between these 2 nodes, you could make a new node. And if we wanted to sandwich it in between A and B, you've got to adjust those arrows. So we can do something like A next equals N. So this points here. And N next equals B. So that points there. And B previous equals N. So this points back here, and N previous equals A. So that points back. And there's your new list. And what I'd like you to think about with this is, before I started writing these lines of code, I labeled my nodes that are involved in this. Here's node A, here's node B, here's node N, the new node, right? If you're asked to write code to insert something after node A, right, you can do something like B equals, struct node star B equals A arrow next. And now I've got a label for this thing. And now when I want to say N next equals B, right, I can just use B. Now if you don't do that, I could say N next equals A next. But I gotta be careful because up here I changed what the value of A next was. So this is where the order starts to come in and can make your code develop loops or seg faults or things like that. You always got the option though, unless that's one of those mean questions that says don't make any new temporary variables, but I'm not going to do that. Right? You always have this option of making temporary variables. And if you're going for the fastest possible code, maybe that takes a little more time, but on a test or something, feel free, right? Don't force yourself to solve too many puzzles that you don't have to solve. So there's a name, there's a name, there's a name, and now this stuff is just what I'm doing with the arrows, right? I made 4 changes, I made 4 lines of code. So that's just an example of kind of a general approach to these things. Order of complexity, I'm not going to worry too much about order of complexity, but I'd like you to understand the basic concept, which is when we say what the O of something is, we're talking about how well does it perform based on the problem size. So this is linear performance. Order n says if you have n pieces of data, you got to do roughly n operations. And classic example of this is something like searching just a random collection of n pieces of data for some item. Right? You got n things in a bag and you want to see if you've got a particular item in there. You got to go through every single item. The more items you have in the bag, the longer it's going to take. If you have twice as many things in there, it's going to take you twice as long. Okay, that's order n. And the classic coding example is an unordered array of integers, and you're looking for a particular integer. Basically got to search every single entry. Now, if you get fancy and you sort your numbers, and you know how to play high-low and do a binary search, you could search that array in log n. Right, so you cut your array in half each time and you search that subarray, and after log n steps you're down to an array of 1, or you found your number. So for a linked list, you got something pointing out like this. If there's a million things in this list and I'm looking for a number, I got to check the first thing, the second thing, the third thing, all the way through the millionth thing. Right? That's an order n operation. So it's like an array. But if I know, for example, that I want to insert after this node, that's an order 1. Right? I make a new node, I have it point here, I change A to point there, 3 instructions. Doesn't matter that there were a billion nodes before here and a billion nodes after here. As long as I know that I want to insert after this node, it's order 1. If I have to find this node, that's order n. Okay, with an array, if this array is sorted and I want to insert after this number, that becomes order n, because all this stuff over here has to get moved down 1 spot to make space for a new number. So I don't want you to feel like you have to memorize these orders of complexity. I want you to understand the concept. Right, so that if there's a question about this, you can figure it out. So that's all I mean by order of complexity of list operations. Array operations and list versus arrays.
Does that mean a hash is order 1 then, since it just...
Theoretically, a hash is order 1. That's why hashes rule. Because regardless of how much stuff you have in there, ideally it's a fixed set of operations. And a try is also kind of like order 1, assuming your words don't get arbitrarily long. If every word has 12 or fewer characters, it's 12 operations. Just search for something, store something.
Saves a lot of space though.
Yeah. And hashes take a lot of space too. If you really want to maintain order 1 on your hash operations, your hash array has to be infinitely large.
Yeah,
So.
that's true.
All right, so star and ampersand and dot and arrow. So I think everybody's pretty comfortable with these, probably more than in September. So star is basically dereferencing. It's saying take the thing that this points to. Ampersand is saying give me a reference to this, give me the address of something. Right, so star is what are you pointing to, ampersand is where are you stored. And then period and arrow we already talked about for dereferencing fields in a structure. If it's a pointer to a structure, use the arrow. If it's just a structure, use the period. Pass by value, pass by reference. So C is always pass by value. Right, and all that means is if I call some function and I say function x, and previously I said x equals 7, when function is called, it's past the number 7. It's not past x. My function knows nothing about this variable x. All it knows is someone called me and the argument they sent me was 7. Right? If I had said y equals 7 in function y, nothing changes. Right? When I get in function, all it knows is someone called me and the argument is 7. That's pass by value. Pass by reference, when I say function x, it would kind of throw an ampersand in front. And function would actually have the address of x. So, like this, nothing in our function can change the value of x. If you do this, and I tell my function you're getting a pointer to an integer, right? I can't change the argument value, but I can say, hey, that's actually where x is stored in the main program, and I can go to that location by saying star variable, and I can change the value of it. So this is how we can have a function change a value in the caller. That's why we use ampersands with scanf, for example.
It would be helpful if we knew what you were drawing.
There you go. Rewind everything I just said. So if you call function x, that's like saying function 7. If you say function ampersand x, that's passing the address of x.
Can you pass the address of items inside of structures, or can you only pass the address of structures?
Sure. Yeah, you could pass the address of variable dot x. That should work. But let me... say address of
B.x is initialized, I think.
yeah, what did I call it, x? I got other code in here. Oh, that's weird.
It was not Malloc.
Shouldn't have to be because it's a struct.
I think you're calling the wrong source file when you're writing it.
You're right. That could have taken me like the rest of the class. Okay, cool. And you can also do things like That's kind of weird. But yeah, so yes. All right. So Malloc free val grind, you know all about those. You've been using them. Malloc allocates memory, free releases it. If you use Malloc, you have to tell it how many bytes you want. If you're allocating space for a structure, use size of and the name of the structure. If you're allocating space for an integer, use size of int. If you're allocating space for an array, I recommend the size of the array times the size of the stuff in the array. So if you want, I shouldn't have said size over there. If you want integer array equals Malloc 100 times size of int. That'll get you space for 100 integers. Okay. That is better behaved than I don't actually know if that'll work or not. I think it will work. But if you mess up and you do something like size of array bracket 100, that will totally mess up because that's an integer. It'll allocate 4 bytes. And I saw some people struggling on PA5 with that. So stick to types of variables when you say size of, and if you want multiple ones of them, just multiply by however many you want. Right?
When should you malloc an array versus just declaring one?
Good question. So if I don't know how big my array needs to be, right, if I'm going to open a file and store its contents in an array, I might open it up and read through once and count how many things are in there. And then I could, you know, multiply that value times size of int and create an array. So that would be one place. If you need a really big array, you can get more like this than you can by statically allocating at compile time, because it comes from different places in memory. Those would be the two main ones. All right, GDB, how many people here are using GDB at least sometimes? Cool, okay, good. 223 is almost all Java, so we don't get to use GDB anymore. But we may play with JDB, which is a Java debugger.
That's funny.
Yeah, but I've never actually had a lot of success with JDB, so that's one of my goals over break is to get better with that, so we can incorporate JDB. So GDB, right? Just basic. What's the concept? Basic commands, things like that. No surprises, nothing new since the midterm. Makefiles. So most people are including Makefiles now in their programs. I would like you to know how to make a more than a 2-line Makefile. So some people are turning in Makefiles and they work as Makefiles, but it's basically just one big GCC line. GCC-O PA5 hundreds of things .c, right? That builds your executable successfully, but it's missing the idea of a Makefile. So I'd like you to know how to compile the .c's into .o's, and then how to link those .o's together, right? So you make the objects by saying GCC-C, and then you link those together with just GCC, all of your .o's. Right, so if you're not sure how to do that, we can go over it now if you ask, or go back to your notes, or post on Canvas, and I can post an example or whatever. All right, abstract data types. In Every time we talk about a data structure, a stack, a queue, a list, a trie, etc., right? There's sort of two aspects to this. The one we worry about most is how do we implement this? How do we write code to create a stack or a queue or a tree? But there's a higher level layer, an abstract layer, in which we can think about these data structures. So abstractly, a stack is a place we can store information, and we can pull information back in the reverse order that we stored it. So that the last thing we stored is the first thing that we pull back. And then if we pull back another piece of item, it'll be the one that we stored before the last one.
Like stacking plates.
Like stacking plates, exactly. So that's the abstract view of a stack, right? The implementation of a stack is, well, I've got an array, and I've got a variable called stack pointer, and I initialize to 0, and I increment when you push, and so on and so forth. Or I've got a linked list, and when you push, I insert something in the beginning, and when you pop, I remove. Or I've got a stack pointer, and I decrement when I push, right? Those are the implementation details. As an abstract data type, it's just a collection of data. I can add things. I remove them in the opposite order that I added. A queue, I remove them in the same order that I added, right? So we like to understand data structures both as abstract data types and as things that we can write algorithms and write code to implement. So that's all that ADTs deal with. All right, recursion is going to be a theme. It's been a theme in everything we've done here, and it'll be prominent in 223. So writing recursive code from a recursive definition and thinking of iterative algorithms recursively. So these are two slightly different things. When we talk about the height of a binary tree, we originally said start from the root and count the number of edges to each leaf node. Right? That gives the depth of each leaf node, find the maximum depth. And we could write that by starting at the root and going left and coming down, and when we get to a leaf, we could record what the depth was, and if that's bigger than our maximum, we can adjust our maximum. If we do that to all the leaves, when we're done, maximum depth, that's the height of the tree. That's not how we write our height function, though. Right? How do we write our height function? We use a recursive definition. The height of a tree is equal to -1 if t is null, or 1 plus the maximum of the height of the left subtree or the height of the right subtree. And nowhere in talking about start at the root, see how many edges you go till you get to a leaf, take the deepest node, nowhere in there do we see anything like this, right? But we can rethink what the height means as this recursive definition. It's just one more than the height of the largest subtree, the highest subtree. And there's lots of things we can think of recursively. When we search for something in a tree, we can start at the root. We can say if you're smaller than the root, move to the left, and if you're bigger than that root, move to the right, and the root's equal to your number, so I found it, right? We can move down from the root, comparing each node to the thing we're looking for, but we can also have a recursive search function, which says if my number is equal to the root, or if it's in the left subtree, or if it's in the right subtree, then yes, it's found in the tree. And to see if it's equal to the root, we just say equal. To see if it's in the left subtree or the right subtree, we call our search function recursively. So if we wanted to write our own version of string length, take a string in C and tell us how many characters are in it, we could write a while loop. Right, we could initialize a variable to 0, and we could say, well, character I is not the null terminator, increment I. And when we get to the point where character I is the null terminator, I is the length of the string, we could just return that. But can you think of a recursive way to find the length of a string? And forget about C for a moment, let's just think algorithms. So here's a string. And you want to figure out how many characters are in that string, and you don't want to count them yourself because that's a lot of work.
Just make a count that starts at 0 and then for every case where the array of count plus 1 does not equal null, you just increment the count.
Okay, so that will give us the length of a string. That's a good iterative solution, right, if we want to write a loop. How could we do this without writing a loop?
1 plus the length of the rest of the string?
Yeah. So someone hands me this and says, hey, can you tell me how many characters are in here? Here's what I do. I look and I see, are there any characters in here? If there's not, I'll just say length is 0. Otherwise, I get a pair of scissors, I cut this right here, and I hand this to a friend and say, hey, can you tell me how long that string is? And they come back and they say, there's 17 characters there. And I say, thanks. And I tell the person who asked me, hey, there's 18 characters. That's a recursive version. How could I search a string for a character if I didn't want to write a loop?
Check to see if the first character is what you want. If it's not, pass the rest of the string to someone else.
Exactly.
And ask if
So recursive search for something inside a string, see if the first character is what I'm looking, see if the string's empty. If it's empty, nope, your character's not in there. If it's not empty, see if the first character matches. If it does, yes. If not, search the rest of the string for the character. That's the recursive call. If it's in the rest of the string, then I can say yes, and if it's not in the rest of the string, I can say no. And this is what we do well, not we, but whoever was coming up with these tree algorithms, right? This is the kind of thing you go through. So that's what I mean by thinking of iterative algorithms recursively. Once you have a recursive definition, right? Once you have something like this, you can write code for that. And the code almost comes directly from the definition. So factorial n equals 1 if n equals 1, n times factorial n minus 1 if n is bigger than 1. That's a classic recursive definition. It's 2 lines of code. First line says if n equals 1, return 1. The next line says if n is bigger than 1, return n times fact n minus 1. So most of the challenge in these is figuring out the definition. And if you're given the definition, then it's fairly direct, right? You did this in knapsack. This was PA5. We had a nice recursive definition. I was inside a loop. You had to keep track of max and structures and all that stuff. But the recursion part was just max val, temporary value. All right, stacks, push, pop, overflow, underflow, right? So it's a structure, put things in, they come out in the reverse order that you put them in. You can implement them with an array with a stack pointer that says, where's the last thing you pushed or where's the next thing you're going to push. Different ways to do that. You can implement them with a list. Easiest way with a list is when you add to the stack, you just insert in the beginning of the list. When you pop from the stack, you remove from the beginning of the list. Queues are almost the same, except we've got things going in one end and coming out the other end. Right? That's how we preserve the order. So we usually think of the tail as where we're inserting and the head is where we're removing. And you can implement that with a list, and you've done that in code. And you can choose to insert either at the beginning of the list or the end of the list, and you just remove from the other end. Or you can implement this with an array. And if you have an array, like the stack pointer, you need something to say, where should I insert, where should I remove? But since those are different, you have a pair of pointers. And since you might insert 10 things, remove 10 things, insert 10 things, remove 10 things, do that over and over, right? We connect one end of the array to the other. So this looks like a circular array. Right, that's kind of the image. So hashes we dealt with yesterday. You worked through hashes. The only thing I'll add here, and this is not on the exam, but under collision management, right, we've been dealing with probing, which is if you get a collision, rehash, find a new place to try storing or searching for your key. Different approach is what we call chaining. So in chaining, each entry in our array wouldn't actually store our data, it would be the beginning of a linked list. And everything that maps to this particular location from our hash function, we would just string on to the end of this linked list. So we don't do probing, our hash function just takes something and it gives you an index, but at that location you find some other data structure that can store multiple pieces of information. And so you put these things together in a linked list. That's called chaining. It's another way to handle collisions.
Could you just make that another array with a different hash?
Yep, you can have a hash of hashes like that. And it's not a bad thing to do.
That would be troublesome though, wouldn't it?
I don't know. It can have some good performance characteristics. All right, so we'll start talking about trees and AVLs and tries and dynamic programming and all that stuff tomorrow. Let's go get pie.
I don't eat pie.
I'm no longer vegan, so I can eat pie. Which I'm very happy about.